Wow. Golly, I think we've got something. I better talk to Mark. Hey, Mark.
Hey, David.
We have a new asteroid.
A new asteroid?
Yep.
Well, I better get the STEM and 30 team together then. You know, they scatter after the shows. So let me see if I can get them.
All right, Mark, the whole team's here.
David said a new asteroid's just been discovered.
When's this gonna hit the Earth?
It doesn't hit the Earth. I think we need to teach students about asteroids and NASA's redirect mission.
Well, how much time do we have?
You've got 30 minutes
When do we start?
right now, because this is STEM and 30. This is STEM and 30.
Hi, I'm Marty Kelsey.
And I'm Beth Wilson.
We are coming to you today live from the National Air and Space Museum in Washington, D.C. We're standing right outside the Moving Beyond Earth Gallery.
Marty, why would I want to go into the Moving Beyond Earth gallery?
This gallery is phenomenal. It's one of my favorite in the entire museum. Some of the artifacts in here will blow you away.
All right, you've convinced me. Let's go in.
This gallery is dedicated to the space shuttle and space station era, as well as that of future space flight. On display here are the spacesuits worn by Sally Ride, the first American female astronaut, and Guy Bluford, the first African-American astronaut.
You can visit the middeck to explore a variety of space-flown artifacts, including a can of soda, Buzz Lightyear, and many other items that have flown in space.
And when you come to this gallery, you can't help but notice the amazing models. Hanging from the ceiling is a scale model of the International Space Station, and across the room is a scale model of the Space Shuttle Columbia.
Well, let's start by welcoming our in-house audience, Whittier Education Campus. Thank you all for being here today.
We'd also like to thank all of our online viewers and those watching on NASA TV. If you go to our website, be sure to submit questions that we will have a docent standing by ready to answer. Some of those questions we might even use on the show today.
So, Marty, why do we want to study asteroids?
That is a really great question. And to help us answer that question today, we have the program manager from NASA's Asteroid Redirect Mission, Dr. Michelle Gates. Thank you so much for joining us today.
Hi.
So, I want to get you guys involved real quick. These guys all in the audience have go and no-go signs. So we're going to talk about a couple of different concepts that we had for the mission at the outset. We're going to ask you to give us a go or no-go for that concept, and we'll see which one they choose. So one idea is to go out into space, find a small asteroid, and grab it and bring it back towards Earth. The other idea is to go out, land on an asteroid, pick up a boulder from it, bring that boulder back towards Earth. Now, both of these are very complex. You have to think about the cost and the safety and all of the design challenges. So let's see what you guys think for go or no-go. How about the first one, going out and grabbing a smaller asteroid, grabbing it up and bringing it back towards Earth? Let's see. Okay. All right, how about the idea of going out, landing on an asteroid, picking up a boulder, and bringing it back towards Earth? Pretty good. They pretty much agree with what's actually happening, don't they? So tell us, which of those ideas was chosen?
Absolutely. So we did decide to go with the option to travel to a large asteroid and extract a multi-ton boulder or cohesive mass from the surface of that asteroid, and then actually perform a demonstration of a precision deflection maneuver of the larger asteroid and bring that boulder back to the lunar vicinity.
Now, a precision demonstration, tell me what that is.
So actually what we'll do is utilize the gravitational force created by both the spacecraft and the multi-ton boulder together to slowly and precisely, hopefully we'll measure it, alter the trajectory of the large asteroid while it's hurtling through space.
So you're actually looking at planetary defense here, so that if there ever is an asteroid headed towards Earth, we can go out and nudge it maybe just a little bit so that it misses Earth.
It'll be a demonstration of one type of deflection.
Awesome. Well,
Absolutely.
what are some of the other challenges that this type of mission presents?
So the robotic spacecraft, which you can see here on the front end of this subscale model, is powered by advanced solar electric propulsion, which is a combination of advanced technologies, including large-scale, high-power solar arrays, long-life ion thrusters, and power processing and conversion technology. It's the integration of these technologies that provides the real enabling system for this demonstration, as well as the integrated demonstration of moving a multi-ton mass through solar system interplanetary-like trajectories.
And a lot of this is brand new technology.
Yes.
That is-
Yes. It'll be the first time it's flown. We call it a capability demonstration.
That is awesome. So, tell me something else about this mission. The solar panels are super high powered?
They're much higher powered than anything we've flown before.
That is awesome. I love the idea that you guys are creating new technologies and putting them together in a way that we're able to do all kinds of different things. You ready to take some questions?
Sure.
All right, we're going to start with a video question.
Hi, my name is Lizzie, and I'm from South Valley Middle School. My question is, what are you going to build to get the asteroid back to Earth?
Thanks very much. So in addition to the solar electric propulsion system, there's actually a capture system on the front end of this model and will be on the spacecraft. The capture system includes two sophisticated, mature robotic arm technologies, as well as a contact and restraint system, which you can see in the gold here. Some sensors are actually common sensors with some other applications, so we're trying to infuse some commonality and efficiency into our overall build philosophy at NASA. And it's the combination, again, of those technologies that allows us to grasp and acquire and lift off the large asteroid with this boulder and carry it back to the lunar orbit.
Awesome. All right, we've got an audience question now.
Hi, my name is Kamavra, and how long will it take to get to the asteroid?
Thanks very much. So our current trajectory plan is approximately 18 months. It is not a short mission. That is one of the advantages of utilizing solar electric propulsion, in fact, is it provides some flexibility by allowing a very low thrust, which is a rather slower and more flexible thrusting technique than we use with our big engines.
Awesome. Now we've got an online question next. What will happen to the asteroid boulder when the mission is over?
So we will store the boulder. It's a multi-ton boulder, a large boulder, in the Earth-Moon gravitational system. In particular, in a stable orbit around the moon. The orbit is stable for 100 years or more, 75,000 kilometers or 45,000 miles above the surface of the moon. And after our first mission to that asteroidal mass with astronauts, we actually have some options that can be considered in terms of what would be done with the asteroid afterwards while it's there. A number of options. There may be interest by commercial industry, for example. And so we're talking about options in a strategic fashion.
Awesome. All right, so recently we had an opportunity to go to Goddard Space Flight Center, and Beth talked with Bo Nas, one of the lead engineers on the asteroid redirect mission. Let's go check that out.
I am at NASA's Goddard Space Flight Center, and I'm with Bo Nas. Thank you so much for joining us.
My pleasure.
We have got this very complex thing here. Do you want to tell me what this is?
Sure. This is called a microspine tool. It's the end effector, the tool that we use on the end of our robot arm to capture a boulder off the surface of an asteroid. It has, this version of it has 24 paws, and each of these paws has several fish hooks on the end of it, something like 2,000 fish hooks total. And these fish hooks are used to grasp the boulder so that we can lift it up off the asteroid's surface.
And how do they work?
Well, so you can see that they are individually mounted on these springs so that they can move kind of like cat's paws. Although, except we're not trying to retract them so we don't scratch ourselves. We're trying to make it so that we get as many of them to grasp the little features of the boulder as possible. So this tool is placed on the boulder by the robot arm. These paws are lowered down onto the surface and retracted, and so that we grasp the rock features.
Now this looks very complex. So what are some of the challenges that you have to go through to make something like this, to lift a boulder off an asteroid?
Well, this is a very complicated mechanical device, so there's a lot of work that has to go into making the very precise measurements and metal pieces inside. It also has 7 different functions that it provides. So I told you about 2 of them. One is this raise and lower. One is the pull in. In the flight version, it will have a drill that drills into the rock to provide additional anchoring.
Okay.
It can, after it drills, it also hammers to get down into the rock. So if you've ever tried to drill into cement, you know that that's difficult. Of course, this tool also has to accommodate a wide variety of rock surfaces, rock types. We know a good amount about asteroids, but one of the things we definitely know is that there's variety, and we won't know the details of what this rock is going to look like until we get there. So this tool will have to accommodate that wide range. We'll fly it down to the surface autonomously. We're 30 minutes away round trip by light from Earth. So the entire sequence to descend down to the surface with this is autonomous, and the spacecraft does it all by itself.
That is really cool.
That interview was gripping, but that's not the only part of the mission. The next part of the mission is to actually send astronauts out to the piece of the asteroid that we bring back and put in orbit around the moon. Can you tell us about that?
Sure. So the aft end of this integrated vehicle stack here is the Orion space capsule. And our plan is to, and we plan it, is to take the astronauts on the space capsule approximately 75,000 kilometers further from the moon, which is about 45,000 miles further than we've ever taken astronauts before. Rendezvous with this solar electric propulsion space vehicle and execute a number of EVAs, or extravehicular activities, to select samples, acquire samples, contain samples, and return them to the Earth with the crew in the Orion capsule.
So when we look at this model, we're actually looking at 2 separate spacecraft here, one that's going to go all the way out to the asteroid and the other one that's going to bring the crew up and then dock with it.
Right, exactly. And it's the ability to separate those functions into 2 separate spacecraft that allows us to do a number of things within NASA from an engineering perspective. One is to lower the risk to the crew while lowering the cost to the portion of the mission that actually performs the portion that is less necessary to have the crew for, but provide an integrated capability demonstration for us to continue to take our astronauts farther and farther than we ever have before.
That is so cool. Well, recently I had an opportunity to talk with astronaut Randy Brezhnev about some of the training that he's done to actually go out to an asteroid. So let's check that out. I am joined today by Randy Comrade Brezhnev. He is a space shuttle astronaut. He also did 2 spacewalks that totaled over 11 hours in space. Thank you so much for joining us today.
My pleasure.
So there are some challenges when you do a spacewalk. Can you tell us about those?
Well, first, obviously, is we have to have a spaceship to go outside. It's got to be able to have a breathable atmosphere. It's got to be able to maintain the temperature because, as you know, it's plus 250 degrees in the sun and minus 250 degrees in the shade. So that 500-degree temperature change is pretty substantial to overcome mechanically.
Now, what additional challenges will there be for a spacewalk that's way out from Earth, maybe in orbit around the moon?
I think probably the biggest thing is when we're doing spacewalks here in low Earth orbit, you've got the Van Allen radiation belts protecting you from the cosmic radiation. Outside of the Van Allen radiation belts in lunar orbit or anywhere else, we don't have that. And so the radiation exposure in those suits is going to be a lot more. And so I think we'll have to have suits that are designed for a higher radiation environment I think psychologically, the more human part of the harder part will be the fact that you don't have Earth, this big, huge ball right there. So even though you're 220, 250 miles up when you're doing a spacewalk for the space station, you still have the feeling you're tied to Earth. So the moon guys, where they could put their thumb up and cover the Earth, when you're that far away, you don't have the Earth there, that might be a different sensation from the falling one that you might have to overcome.
Now, you've done some training for actually working on an asteroid, correct?
Correct.
Can you tell me about that?
Well, what we did was we used the NEMO missions, the NASA Extreme Environment Mission Operations, is what we call it, and where we lived in the Aquarius habitat off the coast of Florida, the only undersea habitat left in the world, and we lived there for a week underground simulating a Mars mission. Part of our time was dedicated towards equipment exploration that would allow us to do work on an asteroid, because asteroids are small. They don't have gravity, so if we go up to an asteroid and one small enough that we can do in the asteroid redirect mission, capture it and bring it back to the Earth-Moon system, if we go up to it, well, we're going to push it and it may push away or it may push us away, but we'll be opposing each other. And so what we did was they were working on a system that we could actually try and bolt down to the surface of the asteroid and then using a telescoping arm actually then drill into the surface to get core samples, determine the composition of it that'll give us the history.
Now, that seems like it's going to be a challenging mission. Would you like to be on that mission?
Oh, absolutely. I mean, that's all astronauts want to go do, the neat, hard stuff you haven't done before, because that's the fun thing about learning. It's the fact that something's interesting to you. You go study it, you work hard, and then hopefully in the end you can either find the answer, or in this case, with exploration, develop and figure out how we go further based on the answers we find.
Awesome. Well, thank you so much for taking the time to talk with us today.
My pleasure.
Okay, so I'm sitting here with my friends. Now, we just heard an astronaut talk about traveling into space. How many of you would like to be on one of these missions? Let's see, go, no go. I think we have a lot of goes. All right, I think we've got a lot of people who do want to be astronauts. Now, you all had a chance to meet with Marty, right? He came to your school. Do you want to tell us what he did?
Well, we study more about meteorites and where they come from, and we studied rocks, and the texture of it was very smooth. We were able to use magnets to attract the pieces of the meteorites.
Okay, so do you want to take a look? Let's take a look at what you guys did. Okay?
I'm at Whittier Education Campus, and today, are you guys ready to become geologists?
Yes.
All right, so we're going to check out some rocks, but these aren't just normal, ordinary, everyday rocks. These rocks are from outer space. Whoa. These are all meteorites, chunks of asteroid that at some point fell to the Earth's surface, and we have found them, and now we can study them to learn about our early solar system. So you guys ready to check these out?
Yes.
All right, let's go do it. So this was originally a meteorite made up of a whole bunch of slices like this, and then they sliced it so that they could study the inside of it. Meteorites are made of all kinds of different things, and you guys have two very different ones here. This one is mostly made of rock. So what we know from this one is that this type of meteorite was probably from the outside layer of an asteroid, where this one that's mostly, feel that, it's mostly metal, iron, very heavy, is most likely from the inside of an asteroid. And what's really cool is here on Earth, we don't really have rocks from the very inside of the Earth, do we? No. But here we have a rock from the inside of an asteroid. And then we can learn a little bit about how that asteroid was formed or what that's made out of. Guys, did you think it was pretty cool getting a chance to hold rocks from outer space?
Yes.
Now, they were a lot heavier than they looked, weren't they?
Yes.
So good job today. I've got to say, you guys and your observational skills, you rock.
Thank you.
And I'm here with Lindley Johnson. How are you today?
Good, good.
And you're going to tell us a little bit about asteroids.
Yes. You might ask, why are we interested in exploring asteroids and getting materials back from them? Well, asteroids and their distant cousins, the comets from the outer solar system, those are literally the construction materials of the solar system. If you go by a building construction site, you see these piles of sand and bricks and rocks. Well, an asteroid, I think we have an image of an asteroid here, that looks a lot like construction material.
Cement.
From a construction site. And so this is a material that over the course of the solar system, the billions of years of the solar system, has coalesced together and grown bigger and bigger and become planets of the solar system. So by going to an asteroid and sampling material and bringing it back for laboratory analysis, we can literally determine what elements built up the solar system and became the planets, and material that possibly has the elements for the creation of life. Now, the asteroid that I had in the image, that is the one asteroid that we've had a spacecraft have to actually go to an orbit and collect samples. It's called Itokawa. It was visited by the Japanese Hayabusa mission. And it's, in real life, it's about a quarter mile long. So it's about the size of a football stadium. And so this is a 3D model of it, and as you can see, it has boulders on the surface. It makes a perfect kind of asteroid that we'd want to go to with the asteroid redirect mission to collect samples. We have another asteroid mission called OSIRIS-REx. It's going to go to an asteroid called Bennu, and this is a model of it. It is also about a quarter of a mile in size, but it's looks much darker, and that's because it's a carbonaceous, what we call a carbonaceous asteroid. It has carbon and water and those kind of materials, and possibly by taking samples and bringing them back to Earth, we will discover where the elements for the creation of life came from.
So by studying asteroids, we learn more about ourselves.
Exactly. We are the stuff of asteroids.
Okay. I think we have some questions. Do we have a video question? Let's start there.
Hi, my name is Allie. I'm from South Valley Middle School, and my question is there some way to find out where in space asteroids are formed?
Well, sure, and that's one of the programs I lead at NASA, the Near-Earth Object Observation Program, where we're trying to find where all the asteroids are in the solar system. So we take the observations, we determine what their orbits currently are around the sun, and then using math, computers, thankfully, the computers, we can then back those orbits up for millions of years and determine where in the solar system these objects originated.
Okay, we've got an audience question.
Are meteors valuable?
Are meteorites valuable?
Meteorites are very valuable because that is sort of like a free sample return. When the material that are meteorites, that actually comes from the asteroids and the comets in the solar system. When they pass by the Earth, they leave this material that comes into Earth's atmosphere. So out in space, it's an asteroid, or if it's a very small asteroid, we call those meteoroids. And as it enters the Earth's atmosphere and makes that bright trail as it comes in, that's called a meteor. Okay. And when it hits the ground then and is collected off the surface, that's a meteorite.
Okay.
And so this is material that's been delivered to the surface of the Earth from space.
Okay, let's take an online question. Is NASA worried that if these asteroids aren't redirected, that some of them will definitely collide with Earth?
Well, yeah, that's the real basis of our program, is to find any asteroid that could hit the Earth before it finds us. So our program, it's been operating for about 16 years now, and we have found over 13,000 asteroids that come in what we call near-Earth orbits, and about 1,600 of those are in orbits that come close enough to Earth that we consider them hazardous.
Okay.
So we are continuing to observe those and make sure we understand their orbits, and then find all the rest of them out there, because currently we've probably only found about 10% of the asteroids that could be hazardous to the Earth and can do some real damage if it were to hit the Earth. So this is a program that's going to take many years and literally decades to catalog all those objects.
Okay, thank you so much for joining us today. We're going to go back to Marty and Michelle.
So the asteroid redirect mission is a step towards us heading towards Mars. How does that work?
Yes. So the asteroid redirect mission, again, will be farther than we've ever taken astronauts previously. We'll demonstrate a number of technologies required for the plan to take humans to Mars, including the Advanced Solar Electric Propulsion System, the ability to descend, conduct near operations to a low-gravity body, such as a number of asteroids, which may be along the path to the journey to Mars, as well as the beginning of using staging orbits and integrated vehicle stacks as we learn how to integrate the large masses required for Mars cargo and vehicles to return the crew, as well as the systems that will ferry the crew out to Mars themselves.
Awesome. Well, thank you so much for talking with us today. Now, if you're interested in Mars, you need to be sure to tune in on October 21st as we talk all about Mars. Check this out.
Hi, I'm Beth Wilson. I'm one of the hosts of STEM in 30. And you know what? There's nothing I like more than looking at a great photograph of a beautiful sunset.
Hey, this doesn't look familiar.
Well, it is the sun, and you can see it just sinking slowly behind the horizon here, right along these wonderful mountains. You can almost smell the fresh air. However, there isn't any air. This photograph was taken on Mars by one of the Mars rovers. If you think this is cool, you should check out our next STEM in 30.
So October 21st, all about Mars. November 18th, join us as we talk to the astronauts live on the International Space Station. Thanks to our guests and to NASA for sponsoring our show. We'll see you next time.